All right, folks, welcome back. Didn't think we'd be doing this again. I hoped we wouldn't be doing this again, but times have changed and here we are. We're back doing video instructions. And the reason I'm doing these is because I know a lot of you are starting to be quarantined. Times have brought that upon us. The virus is still at work. And so to get you instruction in probably what I would argue is the most effective way, we're going to do video instructions. As always, email me throughout these if you have questions. Take notes as we go through this. Pause these at any point and email me at any time. So this is going to be the video instruction for section 8.7. Excuse me. We will be skipping section 8.6. If you were here on Friday, or really at all last week, we worked through 8.1, 8.3, 8.4, and 8.5. Those were exponent rule videos. And now we're going to get into applying those exponent rules to something called exponential functions in 8.7. But for now, let's start with this problem. What I want you to do is I want you to pause the video. And I want you to see if you can answer this question and get it right. Make sure you have some mathematical justification to it as well. If you had the option of receiving $100,000 a day for 30 days, or starting with a penny but having that money doubled every day for up to 30 days, which option would you pick? Pause the video and see if you can figure it out. Okay. So let's see if we can solve this problem together. See if you got the right answer. Well, I hope, while it might have been tricky, you at least figured out part of it. $100,000 a day for 30 days. Well, that's easy enough. You're going to end up with a total amount of $3 million. Again, if I get $100,000 a day for 30 days, that's adding 100,000 30 times, aka 30 times 100,000, $3 million. The trickier one to figure out is the penny. But I hope you logic through it something like this. We're starting with 1 cent. Now that's being doubled every single day. So at the end of day 1, if I start with 1 penny, and at the end of the day 1, it doubles, I'm going to have 2 cents. At the end of day 2, I'll have 4 cents. At the end of day 3, I will have 8 cents. And the pattern's going to keep on going. Now, don't make the mistake of putting 1 cent at day 1. Some of you might have done that. We don't want to do that because, well, it's doubling at the end of every day. But if I put 1 cent, that would mean it didn't double on day 1, which it did. 1 cent, our starting amount, almost acts like day 0. I start with 1 cent. At the end of day 1, I have 2 cents. At the end of day 2, I have 4 cents, and so on and so forth. Now, what you might have done is once you recognize the pattern, you said, okay, we're doing 30 days. What he's doing is he's multiplying 2 every single time. And so you furiously multiplied in your calculator by 2 30 times. And you might have gotten the right answer by doing that. But there's an easier way. You see, all of chapter 8, what we've been talking about is this thing called an exponent. And the whole point of an exponent is that it's an easier way of when something is multiplied by itself over and over and over again. So instead of just multiplying by 30 times in my calculator, here's what I'm going to do. We are multiplying by 2 every single day for 30 days, which means I'm doing 2 to the 30th power. Now, if you did this, you got a massive number, and you're very close to being correct. You can't forget the initial part. This 2 to the 30th power is not the total answer, because I didn't start with $1. I started with 1 cent. And what you will have to do is multiply your answer by 0.01, which is the same as dividing by 100. which some of you might have done. In summary, what you can do is we can take our initial amount of 0.01 and multiply it by 2 30 times. But the easier way of writing that, instead of just writing times 2 times 2 times 2 times 2, is times 2 to the 30th power. When you do this, and let me check my work here, what you end up with is $10 million, $10,737,418.24. Much more money than the $3 million. And the reason I had us do this is because I wanted to illustrate the power of exponential growth. What is exponential growth? Well, it's when we increase by a number of times, not a consistent amount. You see, in black, we just simply added 100,000 over and over and over again. But with what's in blue and red, we're not increasing by 2 every time. We're doubling. We're multiplying by 2 every time. As you can see, when you don't just add by the same amount, but you multiply by the same amount, you get a lot bigger numbers quicker. And that's where we're going to go here. 8.7 is all about exponential functions. And so, let's start here. In general, any exponential function is going to have the form y equals a times b to the x. Y equals a times b to the x. And this should look like the formula we just came up with. And my guess is, given the information in red, and given what you see in black, you would be able to tell me that your starting amount is going to always be the letter A. In our penny problem, it was 1 cent. The rate of change is the amount we're increasing by. We're doubling, we're tripling, or maybe we're cutting in half. Maybe we're cutting into fourths. Maybe we're dividing by 8. Either way, B is going to be our rate of change. And X will be our change in time. Our change in time. We multiplied by 2. We doubled our amount of money for 30 days. Any exponential form or any exponential function is going to be in that form. It might look a little bit different. Maybe you subtract 1 from the exponent. Maybe your B value, your rate of change is a little more complicated than just 2 or 4 or 1/2. But nonetheless, they will all share this form. So let's learn to solve some problems with it. We want to evaluate the exponential function for y equals 4 times 3 to the x for y when x equals -3 and 6. Go ahead and pause the video and see if you can figure this out. Evaluate the following exponential function. Okay? You've given it a shot at this point, and what I hope you did is didn't overthink it. You just plugged in the x values I gave you for x and saw what y was. When I plug in -3 for x, what I end up with is 4 times 3 to the -3rd. Folks, this is why we spent so long learning our exponent rules, so that we knew how to work with exponential functions. In the past, you wouldn't know how to solve this. You'd plug in your calculator, probably get some decimal, and be really confused. But you know how to do this. You know with negative exponents, we put them in fractions. So this isn't 4 times 3 to the -3rd. It's 4 times 1 over 3 to the 3rd, which is 4 times 1 over 27, or 4 4 27s. 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 4 27s This is, again, why we learned those exponent rules. How did we evaluate the other one? Well, the other one's a little simpler because there's no negative exponent. Just simply 4 times 3 to the 6th power. Make sure you handle the 3 to the 6th power first. When I do 3 to the 6th power, I get 729 times 4, 2,916. Evaluating exponential functions. Going to look a little different than linear functions, but still pretty easy to evaluate them. So let's apply it to a word problem. Suppose 20 rabbits are taken to an island for an experiment. Biologists want to study how the rabbit population will grow if left to their own devices. The rabbit population triples every half year. The function f of x equals 20 times 3 to the x, where x is the number of half-year periods, models this situation. How many rabbits would there be after 2 years? How many rabbits would there be after 2 years? Well, let's try and figure this out. I'll give you a chance to do it on your own. So as always, pause the video and see if you can figure it out. And then we'll go from there. Okay, you've paused the video. You've given it a shot. So we're trying to figure it out. And it is really just similar to the evaluate problems we've just done. The difference is it's a word problem. And I might not be sure what that f of x means. Please note, we'll learn about f of x a little bit later. Okay, we had to skip that chapter in the interest of time. But just know for now that f of x is a fancy way of saying y. So y equals 20 times 3 to the x. Well, what I know I can do is if I want to figure out how many rabbits there would be after 2 years, I'm going to plug in a value for x, but this is where you had to be careful. X is the change in time. If you look at your definition above, x is the change in time. The temptation here is just to throw 2 in, but we shouldn't be putting 2 in. Why? Because x is the number of half-year periods. How many rabbits would there be after 2 years? What we must put up here is 4. Why are we putting 4 up there? Because x is the number of half years. How many half years are there in 2 years? Well, you could think of it in terms of 6 months. There's 6 months, 1 full year, 1.5, 2 years. There are 4. Folks, I did this on purpose. You must be careful with your change in time. Do not just see 2 years and toss it up there. You must read the context of the problem. So when I solve this, I get 3 to the 4th times 20, and I get 1,620 rabbits. If the rabbits triple every half year, and we start with 20 rabbits, we will end up with 1,620 rabbits. Again, the lesson here, be very, very, very careful with the time value. Okay, last problem for this video. 10 animals are taken to an island every year. The amount of animals quadruples every year. Write an equation to model the situation described above. How many animals are there after 5 years? Use your knowledge of exponential functions and try and create an equation to describe this situation. I'll give you a chance to do it. Pause the video, and then we'll look at it together. Okay, so you gave it a shot. You've unpaused the video. Let's see what you came up with. Well, remember, all exponential functions, as you wrote earlier, are in the form y equals a times b to the x. A is your starting amount. So what do we know is our starting amount? Well, 10 animals are taken to this island. What's my rate of change? The amount of animals is quadrupling every single year. And then x will be whatever my change in time is. So there is a general equation. We've answered this part. There is an equation that models the situation. Now, maybe you already leapt ahead and did it in one step and figured out how many animals there were after 5 years. Well, if we're quadrupling every year, and we want to know how many there are after 5 years, we would plug 5 in for x, okay, since there are 5 years. And there isn't anything special like a half year or quarter year. So we solve this. We do 4 to the 5th power times 10, and we end up with 10,240. If the number of animals quadruples every year, we start with 10. After 5 years, we will have 10,240. Guys, this is the end of the first part of section 8.7. I'm going to break it into 2 videos because I know it's a long section and it's somewhat complicated. In the first part, what we've covered is what is an exponential function, how do they work, what are the different parts of them. And then we solved some problems where we evaluated exponential functions, and we closed out by not only evaluating but creating an exponential function. In the next video, you're going to learn how to graph exponential functions and how their graphs differ than the linear functions we've seen before. Hope you enjoyed watching. Tune into the next video and we'll go from there. Have a great day.